Right, so intermolecular forces. You guys are going to be, I think, fine with this. There are a couple of things that when I read...
Any faculty members who ordered shareware through the activities office, we
Okay.
have those in today.
No, I started the video, so this counts. But there were a couple of things in the essential knowledges that I thought were a little bit different than stuff we covered last year, mainly supramolecular. I'm going to cover that on Monday when we go over some of the essential knowledges and the learning objectives, because there are quite a few that are related to intermolecular forces. We have talked a few times already this year about intermolecular forces, so this isn't the first time this is coming up, but this is where we really cover it in detail. And the reason why is because as soon as you talk about polarity of a molecule, then you're ready to talk about intermolecular forces, because then we could talk about dipole-dipole, London dispersion, hydrogen bonding. You guys remember all that stuff from last year? I'm hoping it's still fairly fresh in your minds because we did it second semester. So, oh, and then for some of you, you might not have learned it last year, just depending. Skip states of matter. Here we go. Okay. So intermolecular forces. This is what I showed you last year, and some of you liked this. It kind of clarified some things from the beginning of the year about the difference between a chemical and a physical change. So break this bond, chemical change, right? Break this bond, that's a physical change, okay? And so basically you just have to realize this is a covalent bond, okay? This is a much stronger bond. This is, electrons are being shared in between these two, okay? And that's what we've been talking about with all the bonding theory we've done. Now what we want to consider is if two HCl molecules come close to one another, they're going to be slightly attracted to each other. Okay, that attraction is not going to be nearly as strong as a covalent bond, but it's going to help these two molecules to actually kind of stick together a little bit. All right? So most of the time when we talk about something being sticky, something sticking to something else, we're talking about intermolecular forces there. Okay, that's how stickers work. That's not how magnets work. Okay. Well, yeah, they are sticking together, but that's how, stickers work. That's how, why am I blanking on other things that are sticky? That's how gum works when it gets in your hair. I don't know, whatever. So I don't know why that came into my mind either, but point is, yeah, when you're talking about, there you go, like viscosity, like thicknesses of liquids. Are the liquids, do they flow slow or do they flow quickly? Those sorts of things are all dictated by intermolecular forces, okay? Boiling points, melting points, vapor pressures, and viscosity. There it is right there. Yeah, you don't need to know van der Waals forces. I'm just mentioning it. You don't need to know it. Forget that happened. But the types of, and the book just insists on calling them van der Waals forces. I don't really care. But the types of intermolecular forces, that's really the term you need to know. Dipole-dipole, hydrogen bonding, London dispersion. Now there is another type that's considered an intermolecular force sometimes, which is the ion dipole. You guys remember from the beginning of the year, that's our ambiguous change, right? Could be physical, could be chemical. It's sort of tough to tell. That's because of the ion-dipole interactions. But these other three, these are definitely intermolecular forces. Now, do you remember which of those, I'll say this, if the molecules are the same size, do you remember which one of these is the weakest of the forces? London dispersion is going to be the weakest of the forces, okay? And then, again, assuming that they're all the same size, the molecules we're talking about, then what would be the next highest? Actually, hydrogen bonding is the strongest out of the three that are listed here, okay? The dipole-dipole interactions would be the next strongest, and then hydrogen bonding would be the strongest out of these three. Ion dipole is, okay, and here it is. That's the fourth type, and that's by far the strongest of the four, okay? So strong that, again, sometimes it's hard to tell if an ion dissolving in solution should be really considered a physical change or a chemical change. Okay, I think I would still definitely argue for physical. But there are some people who would argue that's a chemical. Okay, so then this is what makes it possible for ionic substances to dissolve in polar solvents, because if you think about it, I mean, those ionic compounds, they're pretty stuck together, right? So there would have to be a very strong attraction for the water for them to actually be able to pull apart in the water and dissolve. Okay, so dipole-dipole interactions. This is, I mean, I think these are very similar to the pictures I showed you last year. But I like the pictures. Basically, if you have a positive and a negative end to a molecule, you put it next to another molecule that has a positive and a negative end. The positive is going to be attracted to the negative is going to be attracted to the positive. Positives are going to repel one another, and the negatives are going to repel one another. Okay? So that's the idea with the dipole-dipole interactions. The more polar the molecule is, the stronger the dipole-dipole intermolecular forces will be. All right? Now, I need to say this again, and I can't stress this enough, and I feel like it's shown fairly clearly in the pictures. The covalent bonds are where in this diagram? I'm trying to trick you a little bit here, okay? The covalent bonds are actually inside the molecule itself, right? Okay, those are the ones that are holding the molecule together. So you got to remember, this egg-shaped thing is actually represents a molecule. Okay, the covalent bonds are in there. All of these dotted lines and solid lines, those are intermolecular forces that exist between molecules. Okay, so the dotted ones are the repulsions. Okay, so the dotted ones will go from a positive to a positive, or from a negative to a negative. So you just need to realize, when we're talking intermolecular forces, that's between molecules. All right? If you have one molecule of glucose, you cannot have intermolecular forces. Does that make sense? You need to have at least two glucose molecules before you can have intermolecular forces. Okay? And that's something that students are always confused by. Keep going. Next picture. Okay, well, this just kind of shows an example of these different molecules that have increasing dipole moments. Okay, and dipole moment just is a way to measure the polarity of a molecule. Okay, so the most polar molecule is down here at the bottom, the acetonitrile with a 3.9 dipole moment. Notice it also has the highest boiling point, because you get a bunch of these acetonitrile molecules together. Because they're more polar, they will be more attracted to one another, and it will be harder to pull them apart, which is what you have to do to boil something. Okay? Does that make sense to everybody? London dispersion forces. This is the one that's a little bit tricky, because this happens with non-polar molecules. Okay? Now, everything has London dispersion. Everything. Okay? Not every molecule, I should say. Not everything. But every molecule, every atom is going to have some London dispersion if you put it next to another atom or another molecule. Even dipole or even polar molecules will have some London dispersion as well. Okay, but nonpolar molecules, this will be the only intermolecular force that they have. They're nonpolar; they'll have LDF, London dispersion. You can abbreviate that as LDF. Everybody knows what that means. I've even seen them abbreviate that on their answer keys on the AP exam. So if you want to save yourself some time on the AP exam, write LDF instead of London dispersion forces. So you've got one helium atom. One helium atom by itself, completely nonpolar, right? Okay. But every once in a while, because there's two electrons in a helium atom, right? So those electrons could, at some point, end up on the same side of the atom. And for that split second, this side of the atom is partially negative, this side is partially positive. Remember, we also called these instantaneous dipoles last year? Do you remember talking about that? Because what happens is, it's just for an instant that you have a negative and a positive charge, okay? And then it goes away, because then the electron goes back where it was before, right? So this happens because the electrons are constantly moving. So you'll get partial negative, partial positive for a second, and then it's gone. And then it reappears, and then it's gone. Then it reappears, then it's gone. Okay? So for a split second, you get that partial negative, partial positive. What happens then, if that helium atom that has this instantaneous dipole comes next to another helium atom, now because the electrons are on this side, it's going to repel any electrons that are on this side and cause a dipole in the one next to it. Okay? And so then you get a little bit of a negative, a little bit of a positive. And again, this is just happening and unhappening, happening, unhappening. That's why we call them instantaneous dipoles, because of that. Okay? And so then there's going to be a little bit of attraction between those for a split second, and then it goes away. Okay? This is present in all molecules, doesn't matter if they're polar or nonpolar. Now, if you have polar molecules, they have what's called a permanent dipole. Okay? And that permanent dipole is caused because of the difference in electronegativity of the two elements that are in the compound or in the bond itself. Or it could be more than two elements. Okay? But an example of a polar, like a permanently polar molecule, is HF. Okay? That fluorine is always going to pull the electrons closer to itself. There's always going to be a negative and a positive end to that molecule. But if you've got something like H2, that's perfectly covalent, right? Purely covalent or non-polar covalent, however you want to say it. There is no overall charge on that molecule. There's no overall polarity at all to that molecule. But every once in a while, the electrons might be more on one side of that molecule than the other, and then you end up with London dispersion. Okay? So that's the difference between permanent dipole and instantaneous dipole. Now, the bigger the electron cloud is in an atom or a molecule, the more polarizable it is. The more you can kind of get all the electrons over on one side, and the more of a dipole you'll get when all the electrons are over on one side. Okay? That's its polarizability. So with London dispersion, the bigger the molecule, the stronger the London dispersion that can form. Okay? The shape of the molecule also affects it. Okay? Long, skinny molecules, there's more places where they can be attracted to one another. Okay? And so you got N-pentane with a boiling point of 309.4, because that's a little bit longer and skinnier. If you've got something like the neopentane with a smaller surface area, then it's going to have a lower boiling point because there's just less points of attraction between those two. Okay? So then if you look at this, F2Cl2Br2I2, and I think I showed this to you last year as well. It's kind of interesting to look down the periodic table. Fluorine is a gas at room temperature. Chlorine is a gas at room temperature. Bromine is a liquid at room temperature. And iodine is a solid at room temperature. Okay? And the reason for that is the bigger they get, the more polarizable they are, and the stronger their London dispersion forces. Okay? And the stronger their London dispersion forces, the higher their boiling point, because now they're holding on to each other a little bit more tightly. Okay? So all those I2 molecules stick together a lot better than the F2 molecules, so iodine is a solid at room temperature. Are you doing okay? Yeah. Is this making sense? Yeah. Okay. All right. And we already said that. So question is, which have a greater effect, dipole, dipole, or dispersion? And the answer is, it depends. Okay? If the two molecules are about the same size and shape, then dipole, dipole is a stronger force. Okay? If you get a really big molecule, then London dispersion might end up being the dominating force, because that London dispersion increases with increasing size. Okay? So it really just depends on the size and the shape of the molecule. And that's what I just said. Okay. Sample problem, we don't need to do that right now. Maybe I'll come back to it. But I want to make sure we get through all of this in the time that we have. I've got a lot here. Okay. So we've talked about dipole, dipole. We've talked about London dispersion. We've talked a little bit about ion dipole. We don't spend a lot of time on that. But if you look at these trends, so you look at carbon, silicon, germanium, 10. Okay, so if you're just looking down that group, then you notice there's kind of a steady increase here in boiling point because there's a steady increase in molecular weight, right? But then you look at H2S, H2SE, H2TE, that's a pretty consistent upward trend. But then you've got this weird anomaly here. H2O is much smaller than these others, but its boiling point is much higher. And so the question is, why does this happen? Okay? Does anybody know where this is going? Hydrogen bonding, okay? So what happens with water here, when hydrogen is bonded to nitrogen, oxygen, or fluorine, these are unusually strong attractions, okay? And the reason for that is because of the high electronegativity of oxygen, nitrogen, and fluorine. They don't have the fluorine here, but if you've got something like HF, right? And all three of these have electron pairs, lone electron pairs, when they're bonded with hydrogens, okay? So that's kind of the ingredients that you need to have a really strong attraction, all right? So what happens is, now, you need to understand this. Hydrogen bonding is not this or this, okay? Within a water molecule, those are covalent bonds. That's hydrogen sharing electrons with oxygen, okay? Those are covalent. The hydrogen bond is right here. Okay, and what happens is, basically, you've got this oxygen that's really selfish with the electrons, right? Very electronegative, much more electronegative than the hydrogen. So it's pulling these electrons this way, even though they're technically sharing, okay? This oxygen is fairly negative. This hydrogen is fairly positive, right? Same with this hydrogen down here. So this is a very polar molecule, all right? Now this hydrogen, if it gets its electrons pulled away from it, it's essentially just a proton at that point, okay? It's very small, and it's got a very positive charge. So it's going to be very attracted to anything that's negatively charged that comes along. Does that make sense? So basically what you've got here, another water molecule comes along, there's a lone pair of electrons on that oxygen. Those electrons are very negatively charged. This hydrogen is fairly positively charged, so it's very strongly attracted to that lone pair on that oxygen. Okay? And notice, you've got the same thing on all of these all the way down, right? It's a positively charged hydrogen attracted to an electron pair. Okay? That's how hydrogen bonding occurs. Does that make sense? That's the only way hydrogen bonding occurs is, and we're just going to say with nitrogen, oxygen, and fluorine, okay? And they specifically say on the AP exam, we're just going to focus on those three because those are the ones where you really get this strong bond that we're going to call a hydrogen bond. Okay? Let's see here. So hydrogen bonding, very, very important for a lot of different reasons. Yep, we talked about that. Well, and I think that's pretty much it. Let me see if there's anything else. And then we just got some other sample problems. Oh, and physical properties that it affects. So we can talk about that in a second. One thing I want to talk about with hydrogen bonding, because it's interesting. What are some applications of hydrogen bonding? Some things that come about as a result of hydrogen bonding. Those of you in biomedical classes, you should be able to give me a good one right off the bat.
No.
Unless it's been too long since you've had PBS.
I mean, we're starting 2 years here.
Okay, all right. There are hydrogen bonds in, in proteins because that causes the folds in the proteins, right? And then DNA. You remember DNA? The nitrogen bases are actually hydrogen bonded to one another. That's down the middle, right? So, and you guys have actually talked about that recently, I know, because I talked to Miller about that. When the DNA unzips and it zips back up, You're heating it, you're cooling it, you're heating it, you're cooling it. You heat it up, it gives it enough energy for those hydrogen bonds to break, right? Cool it back down, and then it copies. You heat it, so the PCR thing, right? All right, so anyway, that's hydrogen bonding. Hydrogen bonding has a lot of other applications with just general properties of water, okay? So let me skip over to this really quick. Viscosity, right? How thick a liquid is. Okay, the high surface tension of water is a result of hydrogen bonding. The high surface tension of glycerin and corn syrup. We did this lab last year. Do you remember that? Where we had the water, the glycerin, the corn syrup, and you had to realize, okay, there's a lot more hydrogen bonding in the corn syrup than there is in any of these others. That's why it's so thick. Okay. So it affects the viscosity quite a bit. Surface tension, that's why the bugs can, walk across the water like they can. Okay, and then it gets into phase changes, so we're not going to talk about that right now. But let me go over a couple of these sample problems quickly. How much time do we have? We're pretty much done. Yeah, we don't have a lot of time. You know what? We may have to go over some of these in class. I think that's the basics, and you're going to remember all this stuff. I think once we start getting into it, you may already remember it all. So, yeah, we'll call it quits for now. Oh, yeah, 2:50. We got to stop. All right, see you next time.